What is up, everybody? Um, Today's round 736. This time it's a Div.1 round, and so it's going to be rated for me. So I'm going to be focusing on doing well, you know? Hopefully I do well. If you're competing, then good luck. All right, I'm just waiting for the problems to open. Okay, so there are n nobles, numbered from 1 to n. Noble I is a power of I. There are also m friendships. A friendship between nobles A and B is always mutual. A noble is defined to be vulnerable if both of these conditions are satisfied. A noble has at least one friend, and all that noble's friends have a higher power. Okay. Add a friendship between U and V, remove a friendship between U and V, and calculate the answer to the following process. All vulnerable nodes are simultaneously killed and all their friendships end. It is possible that new nobles become vulnerable. This repeats until no nobles are vulnerable. One can prove that the process will end in a finite amount of time. After the process is complete, you need to calculate the number of remaining nobles. Every process starts with all nobles being alive. Okay. Okay, so we have a graph, and then if for a node, all of its neighboring nodes have a higher ID, then that node disappears. Okay, so let's say we have something that's we have 1 and then 2. Let's assume there's a connection between 1 and 2. We also have a connection between 3 and 4, for example. 1, 3, 4. 2 is a connection to 1. It also has a connection to 4, for example. Okay, so after we remove a node is safe only when it doesn't have actually, well, okay, if someone is alive before then it has a smaller node adjacent to it. But if that had a smaller node adjacent to it, the smallest node adjacent to it can only have this. Wait, so, okay, let's assume there's some friends that are alive and they're connected. So if 2 is alive, then it's connected to 1. But 1 can only be alive if it doesn't have any connections. Yeah. Huh. So I think, okay, my guess is that if at any one point, if a node is connected to a node that has a larger ID than itself, then that node has to die, because at any one point, one of these nodes has to die. And if we process all nodes below the smaller ID, then this ID is basically next. Yeah. Okay. I'm gonna try this. So it's system.out.print sb. Oh, no test cases, just okay. Just n and m. Int n. Int m. And then we have m connections, okay? Where we have int count is equal to new int n. Okay, so we read in 2 integers per line, which is just the 2 nodes. Int a and b, we're doing it 0 index, so let's do -1. And then if, okay, well, let's just count, whichever one is connected is a vulnerable one. So min at a and b plus plus. Int q is equal to integer parse int in file that read So while q is in here, we have the next q lines. Okay, so we have int type. If type is equal to 1, else if type is equal to 2, else. Int res is equal to 0 for int I is equal to 0, I is set n, I plus plus. If the number of vulnerable like friendships is equal to 0, then our answer increases. Otherwise, we just do this. If type is equal to 1, we add a friendship between u and v. Okay. Then we do this, and we remove a friendship. Okay, so we do this, and so it's like count at min at a b plus plus. Count at min at a b minus minus. Oh, so if count at min at a and b, if it's equal to 1, then res decreases. So if this is equal to 0, then our result increases. Okay, so 2, 1. Line 25. What is wrong with this? Oh, it's M. Okay. 2 and 1. And this over here should just be 1. Make sure our variables are all okay. We have n, this is just m, n, and then we're just like doing a bunch of counting. Yeah. If this becomes 1, then our res decreases by 1. If this becomes 0, our res increases by 1. Otherwise, we just query it. Okay. Let's see. I want to read B in the meantime. So a mathematician once said about Indian mathematician that every positive integer was one of his personal friends. Turns out his positive integers can also be friends with each other. You're given an array A of A distinct positive integers. Define a subarray A1, A plus 1 to be a friend group if and only if there exists an integer m at least 2 such that AI mod m is equal to AI plus 1 mod m, which is equal to AJ mod m, where x mod y denotes the remainder. So they have to define a subarray to be a friend group. AI mod m is equal to AI plus 1 mod m. Oh, okay. I see. Well, we know that a friend group of at least size 1 will always exist, right? Okay, well, I think we might want to look at the difference array, because this implies that AI plus 1 minus AI is some number that's divisible by m. Yeah, so I think if it's like, if we can do some sort of like query, like if we take a difference array, then it's just, we want to find the largest subarray with a GCD of at least 2, and we can just binary search on that. Yeah. That's binary search on seg tree. I feel like that should probably run in time. If it doesn't, then that's really unfortunate, but I think it'll be fine. So we get this. We have fast scanner. Is there a way we could do this without a GCD seg tree? And is there a way? Okay, we got A. I was about to ask why the queue is so slow. But we have int t is equal to int file.next int. And n is equal to int file.next int. Oh wait, hold on. This is for each test case. So while t minus minus is greater than 0, system.out Okay, so if we take a difference array, and it's just like the GCD. So how do we represent this? I mean, segtree is probably the easiest way to query this. Or we just use 2 pointers, honestly. Yeah, I think 2 pointers is better. Yeah, 2 pointers will definitely run in time. Let me get my GCD function. New long at n minus 1. And n can be equal to 1. So if n is equal to 1, then we just, answer is just always 1. Array at I plus 1 minus array at I. They're guaranteed to be positive in at least 1. Okay. If it's 0, yeah, okay. So long cur GCD is equal to 0L, and pointer is equal to 0, and then int res is equal to I'm going to find the longest subarray in this difference array that has a GCD of greater than, or of at least 2. Okay, so while cur GCD does not equal to 1, because if it's equal to 0, then that just means we don't have any number in there yet. So while cur GCD does not equal to 1, and or I guess, yeah, it depends on how far it goes, but oh wait, I don't think we can we use 2 pointers for this? Because we have a GCD that like goes up to here, but we also need to maintain how far this GCD goes. And then we have to like remove a number from this GCD. Yeah, I don't think we can I don't think we can use 2 pointers like this. I mean, segment tree and 2 pointers is probably better. Yeah. So we have to build a seg tree either way. Let me do that really quickly. We just like get rid of the binary search part. Long GCD, where this is a GCD function. Let me just get rid of this. Long res is equal to 0. Long value is equal to new long. Combine should return a long. Oh. Long delta. Combine. Wait. Oh. Public long query. Okay. Okay, segment tree looks fine now. So segment tree, seg tree is equal to new. We go from 0 to n minus 1, inclusive. And we just want to update all of these indices. So seg tree dot update with I differences of I. res is equal to, yeah, because adjacent numbers are coprime. Yeah, that makes sense. So for int I is equal to 1, I is less than n minus 1, I plus plus. Raise 0. Yeah, it's possible that, like, even this first number is just 1, in which case we can't do anything. So we have to move this pointer over here. So pointer is equal to min of pointer. Or no, if pointer is less than I. So while pointer is less than n minus 1, and segtree.query segtree.query from I, from I to pointer, as long as it's greater than 1. Okay, so like then pointer minus minus. Okay, so pointer is like the last number that we can choose. Yeah, so if we take a difference between this pointer minus here, where it's like how many numbers can we choose? It's like if we go over here, then we can choose almost one number. But we can actually choose 2 because there's differences. So res is equal to max at res pointer minus I plus 1. 3326. Hold on. Something is not right here. Line 108. What, Stack Overflow? Line 108, how is that even happening? Segtree.query. Segtree.dcd line 104. Wait a minute, hold on. Why is this happening? Print ln a plus b. Oh, is it because of negative numbers? 1 and negative 3. How's that even happening? Oh, absolute value. Ah, true. I did get the absolute value of differences. 3326. Let's make sure we're doing 2 pointers correctly. So if we're at, so pointer should then equal to the first index, such that going from I to the index will have a GCD of 1. So it's like this subarray. Yeah, so it's like this subarray. Yeah, I think it's fine. Are you going to load or not? This is D. This is C. This is D1. Please load. Let me go to M1. Round 736. Integers have friends. going to submit this to problem B, and this is in Java. Okay. Oh wait, so I have submitted it. Where's my verdict? Okay, we got B. Okay. Wait, what's the time limit? Or like how long did it take? That's fine. Okay, so we have A and B so far. C and then D1. And CF is just broken. Okay. I really hope the round doesn't become unrated. That would just suck. 3 little pigs from all around the world are meeting for a convention. Wait, is it loading? Whatever. 3 little pigs from all over the world are meeting for a convention. Every minute, a triple of 3 new pigs arrive on the convention floor. After the nth minute, the convention ends. The Big Wild Wolf has learned about this convention has an attack plan. At some minute in the convention, he'll arrive and eat exactly X pigs and will get away. Wolf wants Gregor to help him find out the number of possible attack plans that involve eating exactly X pigs for various values of X. 2 attack plans are considered different if they occur at different times. The set of little pigs to eat are different. What does that mean? So we query a triple of 3 new pigs. Oh, okay, I think I see. Yeah. I'm assuming there's a really big queue right now. Oh, not that big of a queue. Okay. Problem. Okay, so you choose 1 minute and then eat exactly X pigs. Okay, I think I see what this is asking. Yeah, I think I see what this is asking. So it's like for it's like out of every possible set of the wolves that we, or like the pigs that we eat, how many times can we choose to take them? That might be a better way to think about this. So it's like at every minute, or I guess we should think about, for some set of pigs, we really only care about the the latest pig to arrive. Yeah. So how many sets of pigs exist for this? And then we might be able to do some sort of DP where it's like DP at time is equal to number of sets of, oh, but we don't know how big we want the sets to be. So we have to figure out a way to query it. There's only 3 pigs that we have to. There's only 3 pigs per minute. Like exactly 3 pigs. So it's like the set of pigs that they eat. So let's solve it for only one query. It says dp at time is equal to number of sets of pigs. Yeah, and then it's just like dp at t. We also do like dp at t is equal to dp at the previous time stuff. Like it's basically just an O of n dp. Yeah. O of n per query. So if it's O of n per query, if it's O of n per query, what do we do then? I have to close my door because someone's playing piano right now. Okay, so O of n dp is kind of obvious. I guess we just have to find a pattern, right? Since n and then q. Okay, if we can solve... Wait, can we, if we solve for the max case, can we solve for all cases? So like, if we do number of pigs the wolf will eat in the ith query. Wait, yeah, I don't think it actually matters because 3 pigs arrive at every minute no matter what. Even if like n is 10 to the 6th but we query like 900, it's basically the same as n is equal to 300 because only 900 pigs would have arrived at the time anyway. Yeah. Yeah, and at every minute only 3 new pigs arrive. Okay. So if we do that, or like if we think about it like that, then maybe we just want to try to solve the naive version and then see if we can find a pattern. Yeah, I think that's a good idea. So if it's something that's like NQ and then X, static final. So if we have if we have X pigs, place we can eat this many number of pigs, plus like that many number of pigs, and so on. Yeah, but if it's here, 1562468. Wait, so why is this a little different then? Number of pigs you will eat in the ith query. Eat exactly x pigs. Oh, it's x pigs among all set of. Oh. Oh, okay. So if you just think about it in terms of subsets, then it's just n times. Yeah, because 3n pigs to choose from. I mean, we can't just do an O1 because two sets are also distinct if they're last pig. If they're if like they occur at a different time. Yeah, so like at time I, we come here and then we eat like this many number of pigs. Okay, I see what's going on now. So for all I, find some of NCRs. Like out of 3i pigs that currently exist, we want to choose x of them. So we want to start from 1 less than I, and it goes all the way to n. So is it just finding a pattern then? It probably is. So it's like, let me look up, I feel like hockey stick might be useful here. Hockey stick identity. Okay, well actually I should probably just expand this first before I do that. So it's like NCR 3x plus NCR at 6x plus ... all the way to like sum I over x. Yeah, we want to find the sum of all this. Actually, I don't know if hockey stick would be useful. Maybe not. Okay, what if at every minute 1 pig came instead of 3? If it was 1 pig every minute instead of 3, how would we do this? If it was 1 pig instead of 3... Then it would just be like 1 over x plus 2 over x. And it's just like a sum of that, yeah. All the way to like this. Oh wait, then that would be hockey stick. Yeah, because hockey stick identity is like for some fixed, it's like for, yeah, it's like for some fixed b, we go like a from like 0 to that. Huh. Pascal's a triangle, NCR. I want to look at what it looks like. Okay, so if it's like 3, choose some x. Let's just say that x is 4, for example. So it's like 3, choose 4. I mean, it doesn't exist, so it's just 3, choose 4 is just 0. Yeah. Okay, that's kind of stupid. Let's do 3, choose 2. It's like choose 6. Choose 9. 9, choose 2, and like so on. So it goes along some diagonal. So it's kind of similar to hockey stick. It's just that, yeah, it's kind of similar. It does, it goes by every 3. What if I just Google this? So find sum of NCR 3x. Or like 3I and then x. Actually, wait. Oh yeah, yes. Okay, so what is, for example, three choose 2 is equal to, okay, what is like, 3 choose 2 plus 6 choose 2 plus, okay, well 3 choose 2 is equal to 6. 6 choose 2 is equal to 15. 9 choose 2 is equal to 9 times 8 over 36. 3, 6, 9, 12 choose 2. That's like 12 times 11 over 2. 66. 14 choose 2. That's just, or 15 choose 2, my bad. 105. Maybe 2 is not like the best number to choose, but this couldn't give anything anyway. Okay, well, how do we do this then? Okay, so 3I and then x versus like I and then x. So if it's something that's like, let's look at 3 for some, okay, let's just say for some term k, 3k at x. We know it's easy to find the sum of, if we can easily find 3k minus 2 at x and 3k minus 1 in x, if we can easily find those numbers, then we can find like this last one. Yeah. Let's just say, for example, it was like, let's just say it's choose 4. And then I just say this is like 7, 8, 9 is like 7 choose 4. It's like 7 times 6 times 5 times 4, because we want to choose 4 numbers. And then it's like plus 8 times 7 times 6 times 5 plus 9 times 8 times 7 times 6. And this is all over 4 factorial. Huh. That's interesting. So if it's like some, if everything gets multiplied like this, if we answer everything in distinct queries, then it's like this number, it's like this number shifted over, this number shifted over again. Oh, it depends on what this number shifted over is equal to. I don't know. Maybe that part isn't. Maybe. would they give only 1 second time limit? Okay. I'm running out of scratch paper. Let me screw it around with this a little bit. So if we have I guess if we have something that's like this and then like this plus 1. Yeah, so if it's like 3 to the k, or if it's like 3 to the k plus 1. Maybe I can just find a pattern by printing stuff. Maybe that will be a little bit easier. Okay, so I probably need to generate factorials. And it's up to 10. Oh, it's up to 3 million. It's kind of a lot. That's kind of a lot. Static fact inverse factorial. Factorial I minus 1 times I mod inverse factorial at max minus 1 is equal to power fact at max minus 1 mod minus 2 mod 4 and I is equal to max minus 2 I is up to 1 inverse factorial at I plus 1 times I plus 1 mod. Okay. N is always fixed. What if we just do prefix sums? Oh wait, prefix sums just work, right? Maybe? No, they don't, because the X changes. Yeah. Like, the part that changes, it's hard to define as a prefix sum. Yeah, because if X were to say increase by 1, the denominator would basically stay the same, but the numerator, it would be, like, some terms would be multiplied by, like, a number. Like, this would be, like, multiplied by 6, this would be multiplied by 7, this would be, like, by 8. That's just, like, that's not very easy to show. Okay, these are small enough to where, like, it's not affected. I just got rid of all my input, like, logic. Hold on. Buffered. Okay, in N and Q. Int x is equal to integer of %. Okay, so just that. let's answer this in O of n. I just want to make sure that this is okay. I is at least 3, I is at most n, I plus plus, res plus equal to NCR. So out of n, no, out of I choices, we want to choose x of them. Public static void NCR and A and B. So if A is less than B, then return 0, otherwise we do this. Let me just make sure that this is correct. Hold on. There's probably something I'm just not generating correctly. Oh wait, it's 3 times n. I plus equal to 3. Okay, let's try this again. 961, and then like these numbers over here. Okay, so the numbers themselves are correct. The hockey stick where NCR of I and X is equal to wait, what is it? Yeah, it's basically equal to, if it goes up to n, then it's like NCR of, if it goes up to k, then it's like k plus 1 to like x plus 1, I think. Yeah. I want to see if there's a relationship between this and hockey stick. Like NCR of like up to 3n plus 1. NCR of like 3 times n, because it goes up to this, plus 1. And then we do x plus 1. Is there any relationship you can see? $560. Three times n plus 1 x plus 1. Wait, how can it be different? If it's like a sum of, oh, I guess there's just like a limit, right? Yeah, like once it gets large enough, it just doesn't matter anymore. Same thing over here, except it starts from 1. It's just, we do this. These should be the same value. Okay, yeah, they are. I'm gonna go to the bathroom. to choose at most 8 elements. If we choose at most is there some sort of way we could do DP where it's like the number of ways, okay, like I guess, or X. This is if we ate a pig. Okay, let's assume instead of like 3 pigs arriving in 1 minute, let's just assume that they just arrive at different minutes. Then the answer would literally just be this number over here. And what we would be overcounting is, okay, so among the pigs that have the same set, either 1 pig, 2 pigs, or 3 pigs from like this last minute are created in the set. So like in this last minute that we have, we're going to need to subtract how many, yeah, I guess like how many of these like sets that exist. Yes, like this is like the last minute. Maybe that does something where it's like, if for every like 3K, so among the 3K choices, you want to choose like X pigs, the number of ways we can like choose this. Okay, well if these were like separate values of pigs, like for example, if if only 1 pig is chosen from this last minute, then it doesn't really matter. And that's just like 1 plus like however many we get from these previous things. If we get something that's like that, I want to figure out how much overlap there is. Like how much overcount there is in here. Yeah, this number isn't very obvious. Yeah, probably not. What if it was like 5, I don't know, like 5, 10. We just do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like we just queried something like this. Okay. Yeah, nothing really comes up. Okay, so let's assume we have the sum, we have like an answer to this. Like 3K with X. It's just equal to I guess how many people, or like how many things are equal to that? It's like 3 times k sets of pigs, a number of ways you can do this. Do you want to try to represent it in terms of that? It's equal. Okay, well, like for some value of x, such that it has, how many ways are there to choose a set from here? A set of like 3k pigs. Okay, so it's like out of the set that we chose 1 pig, how many ways are there to choose k numbers from, wait, no, how many ways are there to choose like among those like numbers in here? So like if we, it's like at the last minute that, because we only care about the last minute, we basically only care about the last 3 pigs that we took in some set. If we do that, if we take some pigs in here, like 3k x, and on the last minute, then it's like among, okay, let's just assume that the last 3 pigs have to be taken exactly at this minute. And that means we have 3k minus 3 over x minus 1, or like among these previous minutes. We only want to take 1 pig at this current minute. We only want to take 2 pigs at this current moment. And then our last choice is take 3 pigs at this current moment, which this is basically just equal to like the previous, which is, yeah. Okay. So it's like 3k then x, 3k minus 3x minus 1 plus a number of ways we can do that. Because at this current minute, we don't want to like do that. Or we could also have an option where like we just take 0 pigs in our current minute, which is equivalent to just saying 3k minus 3 over x minus, or I guess just like a previous dp value. Yeah. Because like we have the x minus 1 values over here. Or yeah, if we want to choose 0 values, then we could just do like 3k minus 3 choose x. So that's where this comes from. Yeah, because then if there's like 1 number we can put over here, or like 1 pig we take over here, we have 3 options to take for this pig. At this minute over here, we have 3 pairs of options, and over here we only have 1 option. It's like 1, 3, 3, 1. If it's like that, then how can we draw this? so we either want to find. Oh, we don't have to find a closed form. We could just try to find something that's dependent only on n. Okay, well this is equal to the sum of this, and then this, and then this, and then this. Yeah, so if it's something that's like 3k minus 3, choose x. 3k minus 3, choose x minus 1, and there's 3 choices for the last pig. 3k minus 3, choose x minus 2. Or I guess it's not. Oh, it's not that. It's not this. It's like 1 times. Yeah, it's not necessarily just that though. Or is it? Wait, no, it is. Because this part is necessarily that, but this part is a little bit different. I think. Or maybe, is it? Wait, no, it's not. Okay. 1 times 3k minus 3 over x. Yeah, because we just choose any subset. So if we choose any subset in here, we choose any difference in here, then it could be something like this all over x. How many times does x contribute to that? No, but that's still dependent on x. Yeah, so these are all dependent on like factorials, pretty much. These are just like how many sets contribute to this number. Yeah, so if it's like 3k over, it's like at this number, or like if we choose to enter at this moment. So for any given set of x pigs, I'm gonna read D in case if I know how to do it. Yeah. The only difference in hard problems is that version all coordinates are even. Okay, so I'm assuming a hard version. They can be both odd and even. Okay. In this version, all coordinates are even. There are n fence posts at distinct coordinates on a plane. It is guaranteed that no 3 fence posts lie on the same plane, or the same line. Okay. N fence posts at distinct coordinates. There are an infinite number of cows on the plane. 1 at every point with integer coordinates. You want to build a triangular fence connecting 3 distinct existing fence posts. A cow strictly inside the fence is said to be enclosed. If there are an odd number of enclosed cows, and the area of a fence is an integer, the fence is said to be interesting. Find the number of interesting fences. No 3 fence posts are on the same line. Print a single integer. Number of interesting fences. 2 fences are considered different set of 3 fence points. 3 fence posts. Oh, and the area of a fence is an integer. Okay, if area is said to be an integer, all coordinates are even in the easy version. So all coordinates are easy? Or even, I mean, what does that mean? Oh, I think wait. Yeah, I'm pretty sure that just means that like any 3 points we choose should have a integer area, no matter what. I think that's right. Yeah, so now we can basically just ignore that condition and just say how many sets of 3 points exist such that they contain an odd number of lattice points. Integer corresponding vertices at IB. We know what the area of. Okay, if we know what the area of a polygon is, then we want to know the number of integer points in number. We know it's an integer in here, so let's have an integer number of like same points in here. Okay, so we have a common shared point in here. If we want to have an odd number of strictly inside points, then, I mean, our area could be either even or odd. So it's hard to tell a parity of B just from that. We want it, but A plus if B is odd, then A cannot be an integer, but A has to be an integer, meaning that A minus I plus 1 times 2 has to be an integer. So B does have to be an integer. If B has to be an integer, B has to be an integer. want to think about. Oh wait. Contest has been extended by 10 minutes. Why? Or is that like a late announcement? Okay, well, from the looks of it, it's still going to be rated. I guess it's fine. Hmm. 3 times n plus 1. So if you do this, we'll need to find 3 times n plus 1 x plus 1 minus that. You want to find the sum of I is equal to 3 up to 3n of I choose x. This is the same as saying, yeah, this is like I guess I is 1, and this is like n, 3i times x. This is going to be equal to I is equal to 1 and then n, 3i times x. We know 3i times x is equal to, well, 3i over 3i choose x should be equal to, I guess we could say this is equal to 3i minus 1 choose x minus 1 plus 3i minus 1 choose x. We could do something like that. This is equal to 3i minus 1 over choose x. Can we find this number easily? Like for x and then like for x minus 1. Wait, if we have, if we can find this number quickly, can we find the next number quickly? because x is at most n. So it's like if we can find like 3i minus 1, choose x minus 1 versus like because like dp at 3i and then x is going to be equal to it's basically just dp at 3i minus 1 x minus 1 plus dp at 3i minus 1 and x. The sum of this for like some summation, we can turn this part into if we do I is equal to 1 up to n, the sum of 3i minus 1 over x minus 1, we can say this is equal to I is equal to 1 up to n. Like subtract this. So like 3i minus 2 over x minus 2 plus 3i minus 2 x minus 1. And then eventually we'll like go, I mean this number will always decrease, but this would require us to have access to all of those numbers though. Yeah, and then like this is just equal to, this term is equal to this term is equal to I guess 3i minus 2 x minus 1 plus let's go a little bit further. 3i minus 1 over x is equal to 1 up to n. It's 3i minus 2 over x minus 1 plus 3i minus 2 over x. And then eventually we would just get somewhere that's like x is just equal to like some number plus 3. If we have like 3i minus 2, x minus 1, and then x, but how can we say like 3i minus 1, choose x minus 3? Like 3i minus 1, 3i minus 2. I need more paper. I need a little more paper. Okay. So if we have I is equal to 1 and 3i and then x. Maybe we can like we keep like this term over here, like 3i minus 1 x minus 1 x minus 1 plus the summation of 3i minus 1 and then x. This is then equal to the summation of 3i minus 2 x minus 1 plus the summation of 3i minus 2 x, oh, x minus, wait, hold on, x minus 2 and then x minus 1. Okay, plus the summation of this is equal to 3i minus 2 x minus 1 plus 3i minus 2 and then x. Okay, I want to get these all the way to 3i minus 3. Because then that might be useful. So then over here, this turns into the summation of 3i minus 3 x minus 3. This is like 3i minus 3 x minus 2. This over here is like 3i minus 3 x minus 2. 3i minus 3 x minus 1. This over here is like 3i minus 3 x minus 1. This over here is like 3 minus, or no, x minus 2. Yeah, because like we either subtract minus 3, minus 2, minus 2 on both, minus 1 on the top, minus 2 on both, minus 1 on the top, 3i minus 3, go for x minus 1. And then we just do, this term already repeats. 3i minus 3, x minus 1, or 3i minus 3 and then x. So this appears once, it appears once, it appears 1, 2, 3, 3 times. Okay, so it's like equal to 3i minus 3, x minus 3, like a summation of this, plus 3 times a summation of 3i minus 3, x minus 2, 3 times the summation of 3i minus 3, x minus 1, plus the summation of 3i minus 3 and then x. So yeah, I'm not sure how useful this would look like. Which terms are easy to find? So we only need me like some important values. So we have some values that are like in here. Okay, well, we know. Oh, we can easily find the number of lattice points between any two things. Okay. So we also know the area could be divisible by 4. I wonder, maybe D1 is actually easier because it has more solves right now. E is equal to. Okay, so if we like brute force every like pair of lines, then we can say A is equal to like area by, we could probably use like shoelace for the area. Or like at least use this idea of. So it looks something like this. Yeah, so it depends on, wait, if we know all of these are even, this is a multiple of 4, multiple of 4, multiple of 4. Multiples of 4 minus multiples are 4. Oh, okay. So if every point is even, we actually know that the area is even. So we know A is even in here. If we know A is even, and we know we want I to be odd, we just have to simply count how many are equal to that. Wait, okay. I have an idea. I don't have an idea for C, but I have an idea for D1 that I'm going to try really quickly. So we have X and then Y. Oh yeah, just points. Point public int X, public int Y, A and B. X equals A, Y equals B. I is equal to 0, I is less than n, I plus plus. We copy this. Okay. In this version, they're like, okay. And they're not, those 3 are collinear either, which is nice. New point xy. Okay. So we know that the area of any triangle that we choose should always be even. So this means that if we want the number of strictly enclosed cows to be odd, this is like even minus an odd number is odd plus 1, which is an even number. B over 2 has to be an even number. In other words, B has to be divisible by 4. Okay, so I think we just use a map then, right? Yeah, it's like for each line, we want to look at all other lines that are coming out of it. And then we just want to see, like, if this has like this many, like how many points could like the third connecting line have? The line A to B, okay, like from A to B to C to D, it's something like GCD of C minus A, D minus B plus 1. Or if we're looking at lattice points from AB to CD. So for any like two, so if we're looking, so we like check every line, and then we check every line has like a shared point, I guess. We know how many lattice points are like on this line segment over here. We know how many lattice points are on this line segment over here. That's like really easy to check. I guess the only problem is how many lattice points are on this line segment. Maybe it's like for each line segment. I mean, there's n squared line segments, and we check all endpoints, that's n cubed, which is too slow. It's clear that they want to like eliminate n cubed, like even if it has like a good constant factor. Also, the fact that it's 6,000 probably means they eliminate bit set solutions as well. Because like even if we take this and then it's like, even if we do something like, if we somehow skip all 6 of them, then it's like 6,000 times 6,000 times 1,000 over 64. Oh wait, that actually might run in time. I don't know. If we choose this, no, okay. If we choose that point, and then we get like another point. Yeah, D1 is apparently actually kind of easy, so. So we take this point and this point. There are an odd number of enclosed cows, and the area of a fence is an integer. The fence is said to be interesting. The fence is always going to be an integer. The area is always an even number. So if we know it's always an even number, we know even, there's odd, B over 2, count. Okay. Yeah, I think that makes sense. It's like among all like points going out with like a shared thing. Like we have this going out, this going out, this going out, and like whatever, so on. We know that this, and then this, they have like some number of lattice points. We only care about number of lattice points on them, mod 4. So we split them into 3 different categories. Then we can check how many of these like integers going from here to here are like that. And then among them, number of boundary points on a rectangle or on a triangle should always be like some number. 6,000. All coordinates are even, so we don't really have to care about the area. Count how many triangles exist with interior lattice points. This is equal to, or like the same thing as count how many triangles with divisible by 4. Has to be divisible by at least 4. It's divisible by at least 4. This point goes out like this. Point goes out like that. Number of interesting fences. If we want to look at every 2 lines, right? So we have n lines. For each center point, we want to get about n squared of them over here. Wait, they're all even numbers. Each line has because, yeah. Let me try this. So we need the GCD function to calculate how many points are on a line. So if it's something like this, what do we do then? Yeah, so the number of points, like between any 3 points, if we have like a triangle between here and here, the number of lattice points on here is always going to be even. And it's like, we want it to be divisible by 4. So if we divide everything by 2, we want to make sure that it's even. So in other words, if we take all of these lines and we divide them by 2, we want to make sure that if between like any existing edge, if these are odd, then we want to choose a point that's like not odd. And then if it's even, we want to choose like a point such that it's like all even. It's like odd, then it's like an odd and an even, or it's like both even. Or I guess if it's like even, then they both could be odd. Yeah. Okay, what if we think about it like this? Then each extending thing will either have an odd or an even number. I want to make sure everything has an even number. This will be an even number. Yeah. Whether it's odd or even only depends on the parity of the GCD. It doesn't actually depend on the GCD itself. So like if a pair of coordinates are like, we have like even, we have odd, even, we have even, odd, or we have odd, odd. Odd and odd will match with itself. Like all of these things will match with this, with themselves. Even. Yeah, because it's like if we subtract a number by another number, we always want to change the parity of itself. Yeah. So we always just want to subtract it by itself. So we have like this node over here. If it's like even, yeah, we basically want to know how many lines have like a current point of evenness, as well as like this line extending out of here to have a certain parity. Okay, let me try this then. And center is equal to 0. Center is less than n, center plus plus. Yeah. Divide all coordinates by 2. And then we can say count number of pairs of lines such that it's line point count. We want it to all be even. And point count match. Yeah. So we just like have some things in like a bunch of different categories, basically. Where we have this and this, like how many points are in between here? So we just get 4 and I is equal to 0, I is less than n, plus plus. If I does not equal to center, then how do we want to do this? Alright, well, its parity will be even only when... Yeah, its parity will be even only when this count is equal to even. Yeah, otherwise its parity will be odd. The GCD parity will be odd, and so it's like this whole thing will basically be odd. Yeah, so if we divide everything by 2, then it's like a number of lattice points in here, number of lattice points in here, number of lattice points here should be an even number. Have total even lattice count. So if I is not equal to center, then we have a node such that this and this care about 2 things. We care about its current, this node's position, as well as its distance over here. So like out of the mask, we have int frequencies with a new int. We have basically this extending edge over here can be either odd or even. Yeah, so it's like if the number of lattice points from here to here, we've already divided everything by 2, so we just need to count. Yeah, this number, the first number can either be even or odd, and then the other thing could have like 4 different possibilities, so like 2 and then 4. So center to I, int count is equal to GCD of absolute value of they're all distinct, so it's just point center is equal to array at center. And x is equal to array at I dot x, and y is equal to array at I dot y. Or as point p is equal. GCD of absolute value of p dot x minus c dot x. Absolute value of p dot y minus c dot y. If after dividing, we don't want to add 1 because we know that these numbers are just always going to be some number that's big. So it's just even if there's only like 2 lattice points over here, you only want to count it as a 1. Yeah. And then int t2 is going to be equal to p dot x and 1. Yeah, whether this is like even or odd, 2, 2, 2. And tag 3 is going to be equal to p dot y and 1. And then we do frequency at t1, at t2, at t3 increases by 1. Right? Okay. So how do we do this part? We want to, center to I. Parity of x and y coordinate. Okay, so parity of the x and the y coordinate. From here, we basically just want to count from here to here. What is the current value? Or I guess not the value, but hold on, t1. We only care the parity of this and 1. Yeah, if GCD is odd, then it's odd. If GCD is even, I guess we don't even need GCD, but I mean, it's whatever. How do we calculate this part over here? I guess we could just say, if we have like the count, well, not the count, but A is less than 2, A plus plus. So A is like the first parameter. Okay, so if they have an odd thing, or like, we want the overall sum to be even. Yeah. Like, you want the overall sum to be even. Because then that's when we expand by 2, that's when it becomes 4. So if it's something like this line over here goes out to be odd, then this can only match with itself. Line distance is odd. Then basically, like a first line distance is odd, the second line distance is even. Or okay. So let's assume that we have an even, even, even. Then our options are either, if this is odd, then it's like anything not equal to that. Then, okay, so it's like frequency, if everything is even, then the number of ways you can do this times number of ways you can have an odd distance over here. Plus like anything that's not 0, 1. Or I guess even minus odd. That would still have an, yeah, CDF2 odd numbers should still be odd. So it's just anything that's not equal to itself. Like odd, plus frequency at 1 at 1 at 0 plus frequency at 1 at 1 at 1. So you have this possibility, right? We also have possibility that we have an even and then an even, where it's like frequency at 0, 0 times frequency at 0, 0, 0 minus 1 over 2. So that's like the first option we can have. It's like if one of these choices was 0, 0, 0, like if it had a 0, 0, 0. Then we also have number of ways we want to do 0. Okay, if we have like 0, 0, 1, for example, we've already included all the ways to do it that has at least 1, 0, 0, 0 point. So we do frequency at 0 at 1. Then we only have so many choices we can do. Like frequency at 0, 0, 1. If this is even, if this is also even, then they have to match. But like if this is even, this is odd, then this over here has to be odd. Then it's like frequency at 1, 1, 0 plus the frequency at 1 at 1 at 1. Or we could just like choose itself. And this is the frequency at 0 at 1 at 0 option, where if they have a different thing, then it just has to be different. But we've already included this, so we can only do 1 at 1 at 1. then we can also just choose itself, where it's like 0, 1, 0 times frequency at 0 at 1 at 0 minus 1 over 2. And then our last option is to just like choose among itself. And then we just do this, see what happens. I might have to, maybe I have to divide by 6. That's possible. Okay, I got 2, which is kind of weird. 2 and then 3. Why did I get 2 for this? Oh wait, there's only one triangle in the first place. Yeah. If a triangle existed, yeah, how do I exclude triangles? Or it's like they used this point over here. Maybe instead it's because we've already looked at this point involved, we just want to skip over it. That might be why. And then among here, we can just like choose the correct triangles maybe. Ugh, this is annoying. Phi's plus center. There are 3 interesting fences. There's 1 in here. Okay, so we have about 20-ish minutes to debug this. (216) 3014 is a center. Okay, that's weird. Like 3014 is an even. Oh wait, but this is all divisible. This is all like after it's divided by 2. Yeah, so this is like an odd. Wait, hold on. 30 over 2 is 15. 14 over 2 is 7. Yeah, this is an odd. This is 2 and then 3, so it's like even odd. And then for 2 and 10, it's 1 and 5, so it's like odd. Now these are like the points themselves. But we also want to look at the difference. Like this is a center. If this is a center, then this is like an odd number. This is an even number. P minus x, c minus x, p minus y, c minus 1. Yeah, this is even, this is odd. So like this distance is odd and this distance is even. So if we pick this 3 as like a unit, we should be getting like this distance is odd. One of them distance is odd, one of them distance is even. So we want to connect the even distance. So it should work. It's just, it should actually work. Yeah. So if I is equal to 2, yes. Let me just make sure that this over here, 1, 1, 1, 1, 1, 1. That doesn't look right. Wait, 2, 3, 1, 5. Yeah, I already divided everything by this. No, it's not even an odd and it's not an odd and an even distance. It's wait. Am I doing this input correctly? P 15,7,2,3,1,5. So it's like odd, odd, even odd, odd, odd. Yeah. Yeah, so it should be like even odd and then odd, odd. Why is this not working? P, Y, and 1. It's like it's checking whether it's odd or even. So it's like T2 is P and 1. Let me try this. Oh, if the center is equal to 2. Yeah, that's a little better. Maybe. Okay, so these are different. It's like even, odd, odd, odd. Yeah, okay. So this is, okay, this actually looks correct then. So we just need to check the center point. Or I guess not the center point, but we need to check if frequency, if it's like 0, 1, 1. Oh, right, we need to include, okay, I'm not including everything, that's why. Yeah, like these are just like all odd points, I guess. Yeah, so like if frequency is 0, 0, if there's an even point, then we just have to connect it. If it's an even line, we just have to connect it with an odd line. Or you could like connect an even line with itself. Alternatively, we could do like, yeah, then it's like frequency at 1 at 0, 0. And then we do itself. And we just do frequency at 1 at 0, 0 plus frequency at 1 frequency at 1 at something. Just anything that's not itself. So instead of, so it's currently 1, 0, so we want to do 0, 1. 1, 0, 1, 0, 1, 1, 1, 1, and then we also do it with itself. Okay. And it's just temp plus equal to frequency at 0, 1, 1 times frequency at 1, 0, 0 plus frequency at 1, 0, 1 plus frequency at 1, 1, 0. Yeah. Let's see, is this any better? We are adding more. Oh, shit. Wrong answer. Okay. I'm already dividing everything by 2. If it's odd, odd, even, odd, and then like even, even. Okay, so frequency at 0, we want to do 1s with all masks that are not itself, and then we can do the mask with itself, minus 1 over 2. Do I have to do these with longs? Maybe. And we do, I mean, no, it's at most like 3,000-ish. And we do it with itself, we do it with itself, and then we do it not with itself. 0, 0, 1, 0, 1, 1. We do 1, 0, we have 0, 0, 0, 1, 1, 1. 1, 1, we have 0, 0, 0, 1, 1, 0, and then we do it with itself. Yeah, because if it has an even distance, this last thing has to be even. If it had like an even distance and an odd distance, yeah, we want the total number of lattice points to be equal to that. What if we just flip the parity of this? Yeah, that wasn't correct. Okay, if we have lines going from here to here, what can we do? No, we know the area is guaranteed. Wait, we want the area to be an integer, but because all the coordinates are even, the area should always be even. Yeah, that's like area minus, if we want I to be odd, this is odd, so this is an even number. We want b over 2 to be an even number, so we want b divisible by 4. So in other words, if we divide everything by 2, we just want it to be even. Yeah. So it's like we divided everything by 2, we just want it to be even. So now we want to look at lines like this. Okay, well, every edge is connected to, okay, every point is connected to 2 edges. So if we iterate over this point, that's connected to 2 edges. And it's not hard to calculate that part. P minus x, C minus x. And then it's just, yeah, because then this distance over here, if they were different, then it would be an odd number of lattice points. Or like effectively odd. And then even if it's like an odd plus odd plus odd, it would be an odd number of lattice points, and that would not be good. Is it just long overflow then? I doubt that's the reason why. But I'll try to submit anyway. Okay. 1 0 1 1 1 1 1. Because we want either all of them to be even. So like if this extending edge is even, or we have 2 odds. So if this extending edge is odd, this extending edge is odd. Are we double counting in any way? No. Doesn't seem like it. T2, px and 1, py and 1. It's guaranteed that no 3 are collinear. In version, all coordinates are even. Yeah. Because they're all even, no matter what. This is an even number. This is an even number. This whole thing is going to be even. But we just want the whole, we want to count this to be equal to 4. That way when this is guaranteed to be an even number. It's like an even and even, because we know A has to be even. Because if these are all divisible by 4, we get something divisible by 2. If we get something divisible by 2, then yeah, this is even. Okay, so this line looks okay, this line looks okay. This line looks okay because it's just it minus 1. This line looks okay. This line looks okay. Yeah. This 0, 0, 0. If it's like this even and then it's odd, we needed to match it with anything that's odd in here. One, 0, 1. Okay, this line is okay. 0, 0, 1, 1, 1, 1, 0, 1, 0, 0, 0, 1, 1. And that one looks okay. 1, 0, we have 0, 1, 1, 0 over here. And then over here, 1, 1, 1, or 0, 1, 1. Yeah, so we basically have something has to contain at least 1, 0. Or like 1 even then. Like this looks good as well. Okay, what if I just do, I don't know. We need at least 2 lines in here. And we know that this point, or at least like this point is involved, and like all points involved are greater than it. So if we remove that, then it should be fine. Absolute value, px minus cx, py minus cy. Okay, well, int t1. So if p dot x minus c dot x, okay, well, if does not equal to c dot x mod 2, t1 is more equal to 1. P dot y is over 2 is over equal to 1. Or, oh wait. Oh yeah, that's not true. This is equal to 1, but then this is equal to 0. Then this is just equal to 0. Wait, if this is odd, then what you get is odd. Or 1. This 3, and this is 1. Equal to a new point. Mod this, and this increases by 1. It's like we include this point and this point, but it's possible that this point sweeps up all of these points. If it's 0, then this should be 0. If it's 1, then it should be 0. If it's 2, then it should be 1. If it's 3, it should be 3. Because there's 3 different pairs, yeah. Yeah, because like for each center point, there's like n lines, like n squared ways to pair them. It's like roughly n cubed. Oh, this is supposed to be 0. Right? What? Well, yeah, this was supposed to be 0, not 3. Because we don't want to add it like based on the odd number thing. Wait, well then why is it not giving the right number now? Yeah, because it's like, well, okay, if it's odd, yeah, so if it's, do we ever want to connect an odd with itself? I think that's what we should be asking. Do we connect an odd with itself? Like, do we ever want to do like 1, 1, 0 to like 1, 1, 0? This is 2 odds. Okay. So we do 1 and then 1. Let me try. I think we also connect itself with odds. We do odd and then odd. We do odd and then odd. And then we do odd and then odd. Let's give this a shot. Let's see. Oh, we got it! Oh, clutch! Dude, like on one hand, dude, D was so, I probably should have read D like earlier, honestly. If I read it earlier, I would have gotten a lot faster, but, oh, okay, at least we got it. Okay, that was pretty clutch. I'm okay with that. Like, I spent way too long on D, partly because I spent a long time thinking about C. And honestly, I think if I had a little more time, I think I could get C. But okay. Oh, we got D1. I'm okay with that. I'll take that. I'll take that. Okay. We literally had a minute left, and I found the bug that I had. Okay. Well, I'll probably record Okay, well, first I need to figure out how to do C, and then I'll probably record solutions for the problems that I know how to do. So, see you then.